Welcome to Noah Science, where Earth seems ordinary until oceans fire and fragility reveal improbable survival. This familiar world holds together through narrow margins, hidden feedbacks, and repeated escapes from planetary failure. Earth looks standard for life, yet habitability here survives as a rare exception, not a default. Before blue oceans, Earth endures collision, buried heat and molten violence that should have erased seas. Distance alone solves nothing, because warmth without pressure, chemistry, atmosphere, and timing still ruins worlds. So, habitability depends on more than sunlight. It requires architecture regulation and improbable help from violence. Earth's stability may begin with catastrophe, as a giant impact leaves the moon to steady climates. Deep below the surface, Earth's churning core drives a magnetic shield against atmospheric stripping today. Tectonic restlessness keeps Earth habitable, rebuilding continents, recycling crust, and resisting geological silence for eons. Water becomes an engine shaping rock climate, chemistry, and circulation across the entire planet itself. Once oceans and stone begin interacting, Earth stops being scenery and starts behaving like a system. Life does not merely adapt here. Over time, it rebuilds air, seas, and continents too. Oxygen first arrives as catastrophe, enriching the air for complexity while poisoning earlier life everywhere. Earth nearly freezes into death more than once. Yet crisis keeps revealing hidden resilience beneath. Long habitability emerges from unstable balance, where feedbacks and resets keep extremes from winning outright. But every stabilizing recovery also narrows the margins, making richer worlds easier to damage later. Complex life earns abundance at a price, because delicate food webs unravel faster than form. With humans, Earth gains observers and disruptors, a thinking species now altering planetary habitability directly. Earth's favorable era is only a window bounded by solar brightening, cooling, and change ahead. Earth becomes a rare negotiation among fire, water, rock, air chance, and stubborn feedback loops. Please like, subscribe, and thank you for listening. Because Earth first survives by seeming ordinary. Earth is so familiar that it hides its own improbability. It is the ground under every human story, the reference point for normal weather, normal gravity, normal oceans, normal sky. It is where life happens, and because it is where life happens, the mind quietly mistakes it for the standard outcome. A rocky planet forms, water appears, atmosphere settles, life begins, time passes. But the obvious explanation is not the real one. Earth is not the simple example of a living world. It is the exception that only looks ordinary from the inside. The deeper truth is that this planet seems to stand at the intersection of conditions that are not merely useful, but dangerously specific. It has enough gravity to hold an atmosphere, but not so much that it becomes a crushing giant. It orbits close enough to the sun to keep water mobile, but not so close that the surface becomes a furnace. It forms from violence, survives, bombardment, keeps internal heat, generates a magnetic shield, moves its crust cycles, carbon stores, oceans, and endures long enough for chemistry to turn into biology, and biology to turn into memory. Earth does not merely possess life-friendly features. It somehow keeps them in play at the same time over spans of time so immense that even saying the number dulls the force of it. About 4.5 billion years, that is not a tranquil duration. That is a planetary endurance test. And the first thing to understand is that none of this begins in calm. Earth begins in wreckage. It forms from leftover debris around a newborn sun, from dust and stone. and metal colliding again and again until gravity forces fragments into larger bodies and larger bodies into worlds. The young Earth is not blue. It is not green. It is not a home. It is a hot, battered mass repeatedly struck, repeatedly reshaped its surface closer to a wound than a landscape. Rock melts. Heavy elements sink. The interior differentiates. The core forms. The mantle churns. The crust begins and breaks and begins again. Even the features that later protect life are born in this brutality. The iron deep below the stored internal heat, the restless mantle, all of it belongs to a world still being assembled by catastrophe. This only looks stable from a distance. Up close, the early Earth is a system under construction with almost every major component still in negotiation. And yet, that is only the beginning of the tension. Because even if a rocky world survives formation, even if it cools enough to hold a surface, even if it settles into orbit at a useful distance, that still does not explain why such a world should remain habitable. Distance is not destiny. A place can sit in the broad region where liquid water is possible and still fail in almost every other way. It can lose its atmosphere. It can lock its water away. It can overheat, overfreeze, stagnate, suffocate, or strip itself bare under stellar radiation. Earth is not merely warmed by the sun. It is held inside a narrow operating range by an interplay of rock, air, water, and internal motion that does not have to last, and on many worlds likely does not last. The atmosphere matters. Pressure matters. Chemistry matters. Rotation matters. Internal heat matters. Magnetic protection matters. Feedback loops matter. What looks in schoolbook language like the third planet from the sun is in planetary terms something more delicate, a world that keeps avoiding the simpler failures available to it. Water is one of the clearest examples. On Earth, it exists in all three familiar forms: ice, liquid, vapor. That sentence sounds harmless. It is not. It describes a planetary condition with enormous consequences. Liquid water is not just a scenic feature spread across the surface. It is a mechanism of transport erosion, buffering, mixing, storage, and exchange. It shapes rock. It carries heat. It moves minerals. It enters the sky, falls again, gathers into rivers, pools into oceans, and ties atmosphere to geology in a ceaseless circulation. Where it remains stable, life gains a medium in which complexity can begin. The familiar seas of Earth are not decoration. They are part of the machinery, and because of that, their persistence matters more than their presence. A world can have water briefly and still fail. A world can have oceans and still lose balance. The real question is not whether Earth once acquired the ingredients for habitability. The real question is why those ingredients stay active long enough to become a system, why the atmosphere does not vanish, why the climate does not harden into permanence at one deadly extreme, why the surface does not become geologically silent before life has a chance to deepen its hold. Why repeated crisis does not end the experiment early. Here, the normal image of Earth starts to break apart. The planet is not simply lucky once. It appears lucky repeatedly across different layers of reality. But even that language is incomplete because luck alone cannot explain a system that keeps stabilizing itself through interacting processes. There are engines beneath the scenery. The interior is not dead. The oceans do not merely sit. And life, once it appears, does not remain a passenger. Earth is not just a world that allows life. Earth becomes a world partially transformed by life, which means its apparent stability may depend not on one miracle, but on layers of instability held in check. That is a harder story. It is also the real one. Because once Earth is no longer treated as the default example of a habitable planet, it becomes something more dramatic, a rare world balanced between failure modes, surviving not through simplicity, but through a chain of processes that could have broken at many different points, and sooner or later still can. And behind that entire chain stands an even harsher fact. The Earth, we know, may owe part of its long habitability to an act of ancient destruction so extreme that it should have ruined the young planet entirely. Instead, it helps create one of the hidden structures that makes this world feel steady at all. The next layer of the story begins there. Earth looks old enough to feel permanent, but some of its most important stability may come from a collision so violent that permanence should never have followed it. The surface story is simple. Earth has a moon. It lights the night, pulls the tides, and seems so constant in the sky that it feels like part of the original design. But the real story is not companionship. It is impact. The leading model holds that early in its history, when the young solar system was still crowded with forming bodies. The proto-Earth collides with a Mars-sized object often called Theia. This is not a glancing inconvenience. It is a planetary-scale blow, an event energetic enough to melt vast portions of the young Earth, eject tremendous amounts of material into orbit, and leave behind a debris disk that later gathers into the Moon. What matters is not the event itself, but the system beneath it. Because the Moon is not just a byproduct of violence. It may be one of the reasons Earth remains climatically coherent over immense spans of time. That is the deeper contradiction. A catastrophe helps manufacture stability. The young Earth is already a dangerous place before this impact. The Sun is new. Planets are unfinished. Orbits are settling. The surface is hot, unstable, and repeatedly reworked. Then comes a collision large enough to reset the planet's outer layers and alter its future permanently. In ordinary intuition, this should make habitability less likely. A world struck that hard should become more chaotic, not more stable. But the obvious explanation is not the real one. If the giant impact model is broadly correct, then one of the most destructive events in Earth's early history also creates a gravitational partner, unusually large relative to the planet it orbits. And that partner changes Earth's behavior in ways that may matter enormously. The Moon helps stabilize Earth's axial tilt or obliquity, the angle between the planet's rotational axis and the plane of its orbit around the Sun. That angle is not a trivial geometric detail. It helps define the distribution of sunlight across the planet, influences the intensity and rhythm of seasons, and shapes long-term climatic behavior. Earth's tilt is not perfectly fixed. It shifts over time. But compared with what might happen on a planet without such a large moon, the variation appears more constrained. This matters because an unstable axial tilt can drive profound climatic swings. If the orientation of a planet lurches too far over long timescales, regions that once receive moderate sunlight can be thrown into harsher extremes, and climate can become less predictable in ways that complicate the persistence of stable surface conditions. Earth does experience cycles. It is not a machine of perfect steadiness. But the Moon may help keep those cycles inside a range that complex surface life can survive. This only looks like a detail from a distance. In practice, it may be part of the architecture of long-term habitability. The Moon also powers tides, and tides are not just coastal scenery. They move water, redistribute energy, and in the early Earth may have influenced shallow coastal environments where cycles of wetting, drying, mixing, and concentration become chemically important. Scientists do not agree on a single required setting for the origin of life, and no honest account should pretend they do. But the broader point remains. Tides are one of the mechanisms by which a moon reaches down into a planet's surface environment and alters the behavior of water sediment chemistry and time. The moon is not a passive ornament, it is an active participant in Earth's system. And yet the scale of the original event makes that participation more unsettling, not less. Because it means Earth's present calm may depend in part on a past so violent that under slightly different conditions, it might have prevented calm from ever arriving. The moon's very existence also reveals something harsher about planetary history. Earth is not protected from catastrophe by being special. It is shaped by catastrophe because it is not protected. The solar system of the early era is not a quiet arrangement of finished worlds. It is a crowded field of collisions, mergers, misses, and gravitational rearrangements. Large bodies collide because that is what growing systems do. Some impacts strip atmospheres, some melt crust, some may sterilize surfaces or delay chemical stability for immense periods. The Earth-Moon system suggests that survival is not a clean escape from this violence. It is a reorganization through it. Earth becomes habitable not by avoiding the brutal phases of planetary assembly, but by enduring them in a sequence that does not cross the line into permanent ruin. That is a thinner distinction than it sounds. The moon also slowly changes Earth over time through tidal friction, gradually slowing the planet's rotation and causing the moon itself to drift farther away. Billions of years ago, Earth's days are shorter. The moon is closer. Tides are stronger. Even the daily rhythm of the planet is not fixed but evolving. This is what makes the deeper pattern harder to ignore. Earth does not begin as a finished world and remain one. It is altered by internal heat, altered by impact, altered by orbital dynamics, altered by its satellite, altered by time. Stability is not a starting condition. It is an outcome that has to be maintained while the components themselves keep changing. That is why the familiar image of Earth as a naturally balanced world is too shallow. The balance is real, but the cost is larger. The balance emerges from events and forces that seem just as capable of destroying favorable conditions as preserving them. And that raises a more dangerous question. Even if the moon helps stabilize Earth from above, what protects the planet from a very different threat coming from the sun itself? Ultraviolet radiation-charged particles, solar, wind, atmospheric stripping. A world can have oceans, land, and chemistry, then lose the envelope that makes all of them usable. The next hidden layer of Earth's survival is not in the sky at night. It is deep below the surface, where motion in liquid metal creates an invisible shield that life on Earth almost never sees, yet may depend on constantly. Earth is protected by something no one can see. The air feels immediate. The oceans feel real. Rock underfoot feels permanent. But one of the conditions that helps keep all three intact is an invisible magnetic field generated far below the surface in a realm of heat, pressure, and liquid metal that never appears in the ordinary image of a habitable planet. The surface explanation says Earth is suitable for life because it has waterland and a breathable atmosphere. The real problem is that a planet can possess those things and still lose them. A star does not simply warm its planets, it also attacks them. The sun pours out light, yes, but it also releases ultraviolet radiation and streams of charged particles known as the solar wind. Over long spans of time, that constant outflow can erode atmospheres, alter chemistry, and strip away the fragile outer layers that make a surface world livable. Habitability is not only about receiving energy, it is about surviving exposure. And Earth survives exposure because beneath the crust, beneath the mantle, beneath rock that humans like to imagine as solid and settled, the planet still moves. At the center sits a solid inner core surrounded by a liquid outer core rich in iron and nickel. That liquid metal does not rest. Heat escapes from deeper layers. Composition changes drive buoyant motion, and the turning of the planet helps organize this convective turbulence into a geodynamo. Out of that motion comes the magnetic field extending far into space and forming a protective region called the magnetosphere. This only looks abstract from a distance. In practice, the magnetosphere is one of the reasons Earth is not left naked before the sun. Charged particles arriving from space are deflected, trapped, or redirected. Some spiral toward the poles where they create auroras, one of the few visible reminders that this shield exists at all. The aurora is the beautiful side of the story. The harsher side is what would happen without it. A world lacking magnetic protection is more exposed to atmospheric loss, especially when its upper atmosphere is repeatedly battered by energetic particles. There are subtleties here. A magnetic field is not the only factor determining whether an atmosphere survives. Gravity matters. Atmospheric composition matters. Geological replenishment matters. Solar history matters. But the larger point holds. Earth's protections is not merely a matter of being at the right distance. It is also a matter of having an active interior that translates planetary heat into surface security. What matters is not the shield itself, but the engine beneath it. And that engine depends on something easy to overlook. Earth is not dead inside. It is still cooling. It is still releasing ancient heat from formation and additional heat from radioactive decay within the interior. That persistent internal energy keeps the mantle convecting, helps sustain the core's dynamic behavior, and ties the magnetic field to a much larger planetary restlessness. A colder world is not just a quieter world. It may be a more vulnerable one. This is where the ordinary image of Earth begins to collapse again. The planet seems stable because its continents and oceans feel fixed on human timescales. But Earth's long-term survival depends in part on the fact that it never fully settles. The core circulates, the mantle moves, heat rises. Deep below every forest city, desert and sea, the planet is still in motion, and that motion spills upward into consequences the surface depends on. The obvious explanation for Earth's survivability is its pleasant surface. The deeper explanation is that the surface is being continuously serviced by hidden processes the surface itself does not reveal. Geological stability is not the absence of upheaval. It is the ability of a planet to keep functioning through upheaval without crossing into permanent breakdown. Earth's magnetic history is not perfectly uniform. The field wanders. Its strength changes. The magnetic poles reverse over geological timescales. Lava cooling in ancient rocks preserves evidence that north and south have switched many times. Yet the astonishing point is not that the field varies. It is that the dynamo keeps returning. The system remains alive enough to regenerate order from turbulence again and again. Earth does not offer stillness. It offers continuity through motion. That distinction matters. Because once a planet's interior becomes too inert, the cost may not appear all at once. It may unfold slowly through weaker protection, slower recycling, fading geological vigor, and a gradual narrowing of the range within which surface conditions remain forgiving. Earth's habitability is therefore not just a story of fortunate starting conditions. It is also a story of maintained functionality. A living world in the planetary sense may need a living interior. There is another reason this hidden engine matters. The same heat that helps sustain the magnetic field also powers volcanism mantle circulation and the geological machinery that will become central to the next layer of Earth's story. Because shielding the atmosphere is not enough. A planet must also regulate it. Carbon dioxide must move between air-ocean rock and deep interior. Fresh crust must form and old crust must descend. Nutrients must be cycled. Continents must shift. Mountains must rise and erode. The surface must remain chemically active over spans of time far longer than any species can imagine. A world can be protected from the sun and still fail from within if its outer shell grows too rigid, too stagnant, too unable to recycle the ingredients of climate stability. So the magnetic field is not the end of the explanation. It is evidence of a deeper fact. Earth survives because it is geologically busy. The calm planet of maps and satellite images is built on a moving foundation, and that foundation leads directly to one of the strangest advantages Earth possesses. Its crust is broken into plates that drift, collide, dive, tear apart, and constantly remake the face of the world. On human timescales, this movement feels negligible. On planetary timescales, it may be one of the reasons the oceans remain liquid. The air remains usable and life gets enough time to become complex. The next layer of Earth's durability is not found in the sky above it. It is written into the way its surface refuses to stay still. The ground feels solid because human lives are too short to see how restless it really is. Continents look fixed on maps. Mountain ranges appear permanent. Ocean basins seem like the original shape of the planet. But the real story is not stability. It is motion hidden inside slowness. Earth's outer shell is broken into tectonic plates that drift across the surface, collide, split apart, sink into the mantle, and rebuild the planet over and over again. This is not geological decoration. It may be one of the deepest reasons Earth remains habitable across immense spans of time. The surface explanation says, plate tectonics creates earthquakes, volcanoes, and continents. The deeper explanation is that plate tectonics helps prevent the planet from becoming chemically and climatically trapped. A world can have rock, air, and water and still fail if its surface locks into silence. Earth avoids that silence by refusing stillness. The crust is not one continuous skin. It is a fractured system, riding on a hotter, weaker layer below, driven by heat escaping from the interior. Mantle convection, slab pull-ridge push, and the slow rearrangement of dense and buoyant materials keep the surface in motion. New crust forms at mid-ocean ridges where plates separate. Old crust sinks back into the mantle at subduction zones where plates converge. Continents crash together, crumple upward, then later break apart. Oceans open and close. Supercontinents assemble and fracture. The map of Earth is not a finished picture. It is a frame from a much longer film. What matters is not the movement itself, but what the movement makes possible. Plate tectonics turns the surface into a recycling system. Carbon locked in rock can be released by volcanism. Carbon in the atmosphere can dissolve into rainwater, react with rock wash, into oceans, settle into sediments, and eventually be carried deep into the planet through subduction. That cycle is not perfectly smooth, and it does not act on human timescales. But across millions of years, it becomes one of the great stabilizers of planetary climate. When Earth grows warmer, Weathering can intensify, drawing more carbon dioxide out of the atmosphere and helping reduce the heating over time. When the planet grows colder, weathering can slow, allowing volcanic outgassing to rebuild atmospheric carbon dioxide and restore warmth. The obvious explanation for Earth's long-term climate is that it simply sits at the right distance from the Sun. The real problem is that the Sun itself changes. Over billions of years, it slowly grows brighter. A planet that remains habitable under an evolving star cannot depend on distance alone. It needs feedback. It needs a way to adjust. Plate tectonics appears to be part of that adjustment machinery. This only looks like geology from a distance. In planetary terms, it is climate regulation written in stone. Tectonics also helps build continents, and continents matter for more than scenery. They create shallow seas, coastlines, drainage systems, varied habitats, and exposed rock surfaces where weathering can occur at scale. Mountain building lifts fresh material into the path of rain-wind, and ice feeding erosion and nutrient delivery. Rivers grind continents into sediment and carry dissolved minerals to the oceans. Those nutrients then influence marine chemistry and biology, tying the movement of crust to the fertility of life-supporting environments. A still planet would not just be quieter, it would be poorer in circulation, poorer in recycling, poorer in long-term responsiveness. Earth's surface remains chemically alive because its crust does not get to rest. And yet, tectonics is not a gift without cost. The same system that stabilizes climate over deep time creates disasters in the short term. Earthquakes rupture landscapes and cities with almost no warning. Volcanoes bury regions in ash and lava, release gases that can cool or warm climate, and periodically impose stress on ecosystems at continental or even global scales. Subduction zones generate some of the most violent events on the planet. Continents collide and reshape weather patterns. Ocean gateways open and close, altering circulation and climate across the globe. This is the contradiction at the heart of Earth again. The system that helps preserve habitability is also one of the main sources of danger within it. The balance is real. The cost is larger. Earth does not remain livable by avoiding upheaval. It remains livable because upheaval is part of maintenance. That makes the planet harder to understand and, in a strange way, more fragile. Because tectonics depends on internal heat, crustal composition, water in the mantle, and a set of material behaviors that may not easily arise or persist on every rocky world. Planetary scientists still debate how common Earth-like plate tectonics may be elsewhere, and honest uncertainty belongs here. But even without certainty, the implication is sharp. A habitable-looking planet may fail, not because it never had water or never formed an atmosphere, but because it never developed a sufficiently dynamic way to recycle them against long-term drift. Earth's livability is not a single condition. It is a managed state, and plate tectonics is one of the managers. Over time, this motion does something even more profound. It keeps reshaping the boundary between the solid world and the ocean world. It raises land, builds basins, opens seaways, closes them, changes coastlines and redraws, where water can collect, circulate, freeze, or return to the sky. In other words, tectonics does not just regulate air and rock, it helps govern the behavior of water itself. And water is not a passenger in this story. It is not merely the thing life needs to drink, or the thing that fills the seas and falls as rain. Once water exists in abundance on a planet like Earth, it becomes one of the main operating forces of the whole world, linking sky-to-stone climate to chemistry, erosion, to atmosphere and habitability, to movement on a planetary scale. The next layer of Earth's endurance begins there, with the familiar substance that seems simplest of all and turns out to be one of the planet's most active and transformative powers. Water looks passive because it yields to everything. It takes the shape of its container, falls downhill, spreads across low ground, and seems to accept the authority of rock, air, gravity, and temperature. But the real story is the reverse. On Earth, water does not merely inhabit the planet, it reorganizes it. The familiar image is simple blue oceans, white clouds, rivers, rain, ice at the poles. The deeper truth is that once water exists on a rocky world, in large persistent amounts, it becomes one of the dominant forces governing climate chemistry landscape and the long continuity of habitability itself. Water stores heat, moves, heat, carries minerals, erodes continents, feeds clouds, shapes coastlines, enters rocks, influences tectonics, and links the atmosphere to the deep past of the crust. It is not an ingredient sitting on the surface. It is part of the operating system. That matters because a planet can possess water briefly and still fail. It can freeze too hard, evaporate too far, lose too much, or lock its water into places where it can no longer mediate the rest of the system. Earth's achievement is not merely that it has water. It is that water remains active, circulating through sea, sky, ice, soil, and stone over immense stretches of time. The obvious explanation is that Earth is at the right distance from the Sun for liquid water to exist. The real problem is that liquid water does not just require a suitable average temperature. It requires pressure, atmospheric persistence, and a climate that does not run away toward permanent extremes. It requires enough warmth to keep circulation alive, yet enough moderation to prevent the oceans from escaping into the sky and being broken apart under radiation. It requires enough cold for ice to exist, because ice reflects sunlight and influences circulation, but not so much cold that the planet locks into a frozen stillness from which recovery becomes impossible. Water on Earth is not simply present. It is dynamic across states. Liquid vapor ice, ocean river cloud, snow groundwater glacier. That mobility is the point. Oceans absorb enormous amounts of solar energy and release it more slowly than land, buffering extremes between day and night, summer and winter, coast and interior. Currents redistribute heat across the planet, carrying warmth poleward and helping shape regional climates that would otherwise be much harsher. The atmosphere, loaded with water vapor, moves latent heat from one place to another, turning evaporation and condensation into a planetary heat engine. Storms are not weather layered on top of a stable world. They are one way the world redistributes imbalance. Rain does not merely fall on landscapes, it participates in carving them. Rivers cut valleys, transport sediment, and grind mountains toward the sea. Ice sheets scour continents. Glaciers carry rock like slow machines. Waves reshape coasts, grain by grain. Water dissolves minerals, carries ions, and helps produce the chemical weathering that steadily transforms exposed rock. This only looks like erosion from a distance. In the long story of Earth, it is one of the ways the planet regulates itself. Rainwater absorbs carbon dioxide from the atmosphere and soil, forming weak carbonic acid that reacts with silicate rocks. The products of that weathering wash toward the oceans, where carbon can eventually be buried in sediments and locked away over geological timescales. This process is not dramatic in a single season or a single century, but over millions of years, it becomes part of the great balancing act that prevents climate from drifting too far for too long. Water is therefore tied directly to the carbon cycle, and the carbon cycle is tied directly to habitability. The story on the surface is smaller than the story underneath. Lakes, rivers, and seas are not just habitats. They are interfaces where the atmosphere and lithosphere exchange material and energy. Water in the oceans also influences the deep interior in ways that are easier to miss. At subduction zones, water carried in oceanic crust and sediments descends into the mantle, changing melting behavior and helping drive volcanic processes. Water makes rock weaker under some conditions, influences mineral transformations, and participates in the very tectonic restlessness that keeps Earth from going chemically still. Even here in the deep machinery of the planet, water is not absent. It reaches downward through stone. It alters what stone can do. The contradiction sharpens again. The substance most associated with softness helps sustain some of Earth's hardest structures of planetary function. And water's importance is not only geological, it is biological in the deepest sense. Life on Earth begins in water, or at least in settings saturated, cycled, or mediated by it. Exactly how life begins remains one of the great unresolved questions and restraint matters here. Scientists investigate hydrothermal vents, tidal flats, mineral surfaces, warm little ponds, icy environments, and other possibilities. There is no final single answer that can be stated with certainty. But what is clear is that water provides the medium in which molecules can move, mix, react, concentrate, separate, and try again. It is where chemistry gains room to become process rather than accident. Once life emerges, water does more than host it. It circulates nutrients, supports photosynthesis, enables metabolism, and permits ecosystems to spread from microbial films to oceanic webs to terrestrial systems linked by rain and river flow. Earth's surface is not alive despite water's constant motion. It is alive through it. Yet, for all its power, water is also a source of fragility. Climate shifts alter rainfall. Ocean circulation can weaken or reorganize. Ice can expand or retreat. Seas can rise. Drought can empty landscapes that once seemed permanent. The same substance that buffers the planet can also transmit stress through it. Water is a stabilizer, but not a guarantee. It keeps Earth dynamic, and dynamism is always two things at once: resilience and exposure. That duality opens the next layer of the story. Because once water is present, and cycling once, rock and atmosphere are linked through oceans and weather, another force begins to alter the planet from within that circulating system. Life appears at first microscopic and easy to overlook. But life does not remain a thin film spread across a finished world. Over deep time, it changes the air, the seas, the chemistry of continents, and eventually the meaning of Earth itself. The next transformation is even stranger than oceans on rock. The planet does not merely permit life. It is gradually reshaped by the fact that life is there. Earth does not remain a stage after life arrives. That is the next great break in the story. The familiar version says, Earth forms first, and life appears later, as if biology is something painted onto an already completed world. Oceans exist, continents move, atmosphere circulates. Then organisms emerge and adapt to the conditions they find. But the real story is harsher and stranger. Life does adapt to Earth, yes. Yet over immense spans of time, Earth also adapts to life. The planet and its biosphere begin as separate facts, and then slowly become one interacting system, each altering the other so deeply that the boundary between environment and inhabitant becomes harder to draw. What matters is not only that life survives on Earth. What matters is that life starts changing the air, the seas, the sediments, the climate, and the surface itself. A living planet is not just a planet with organisms on it. It is a planet whose surface history can no longer be explained without them. The first life on Earth is microscopic, and for a long time that smallness makes it easy to underestimate. The world of early microbes seems humble compared with mountains, volcanoes, and oceans. It seems too soft to matter against rock and heat and gravity. But size is not the right measure here. Persistence is. Repetition is. Chemical leverage is. A single microbe changes little. Trillions spread through water mud and mineral surfaces generation after generation across hundreds of millions of years begin to alter the planet at a scale no individual body suggests. This only looks minor from a distance. Up close, life becomes a distributed chemical force. It consumes, excretes, transforms, and builds. It harvests energy from sunlight or chemical gradients. It rearranges atoms. It accelerates some reactions and redirects others. It turns the surface into a place where matter is not merely moved by wind and water, but continually reprocessed by metabolism. This is the deeper transition. Earth stops being just a geochemical world and becomes a geobiological one. Early life feeds on chemical opportunities, very different from those familiar later. The young Earth is not yet rich in free oxygen. It is a planet of microbial strategies, exploiting iron, sulfur, hydrogen, methane, and sunlight in ways that seem alien only because later life rewrites the atmospheric baseline. The obvious explanation is that life simply fits into whatever conditions exist. The real problem is that life once established starts changing those conditions, and not always gently. Microbes form mats, films, and communities. They interact with minerals. They influence sedimentation. They alter the chemistry of oceans and shorelines. They affect what gets buried, what gets dissolved, and what stays mobile in water. In places where life concentrates, the planet's surface stops behaving like sterile rock and water and starts behaving like a chemically restless skin. Stromatolites, layered structures built by microbial communities, are among the surviving reminders of this transformation. They look modest. Their significance is not. They are evidence that life is no longer an accident happening on Earth. It is becoming one of the ways Earth operates. The most important shift comes when some microbes begin using sunlight to split water and fix carbon-releasing oxygen as a byproduct. Photosynthesis in this form is not just another biological trick. It is a planetary weapon. At first, the oxygen does not flood the atmosphere. It is consumed. It reacts with dissolved iron in the oceans and with other reduced materials across the surface. Entire chemical reservoirs begin absorbing this new waste product before the sky itself changes. That delay matters because it reveals the scale of the process. Earth is not transformed by a sudden miracle, but by accumulation, by microbial labor so prolonged and so vast that the surface chemistry of the world is gradually forced into a new regime. The achievement is real. The cost is larger. Because oxygen, so essential to complex life, later is initially toxic to many of the organisms already thriving under older conditions. Before it becomes a foundation of animal metabolism and ozone shielding, it is a corrosive disruption. Life does not move Earth toward a better state in any simple sense. It destabilizes one world to make another possible. That pattern has been forming from the beginning. Fire gives rise to oceans. Catastrophe helps build stability. Water softens rock and drives tectonics. Now life, which seems like the beneficiary of planetary balance, reveals itself as a force that can destroy old balances and impose new ones. Biological processes also help shape the carbon cycle. Organisms take carbon from air and water, build bodies, die, decay, or become buried. Some of that carbon returns quickly. Some is locked away in sediments and rocks, altering climate over long timescales. Life does not stand outside the climate system. It enters it and begins modifying the terms. Even extinction does not erase that role. The biosphere may contract or crash, but it leaves altered sediments, altered gases, altered evolutionary pressures, and altered energy pathways behind it. In that sense, life becomes geological memory. It writes itself into limestone shale iron formations, isotopic signatures, and the composition of the air. The surface story is that living things inhabit ecosystems. The deeper story is that ecosystems across vast time help construct the planet those living things inherit. That is why Earth cannot be understood as a static environment waiting to be populated. From early in its history, it becomes a coupled system in which life and planet co-evolve. Oceans shape microbes. Microbes reshape oceans. Atmosphere influences metabolism. Metabolism rewrites atmosphere. Sediment buries carbon. Burial changes climate. Climate selects survivors. Survivors transform chemistry again. Once this cycle begins, the Earth known to later ages becomes possible, but only by passing through thresholds that do not feel safe while they are unfolding. And the first of those thresholds is among the most brutal. The rise of oxygen is often remembered as progress because later life depends on it. But for the Earth that exists before it, oxygen is not a gift descending from above. It is a planetary shock, a biochemical invasion, and one of the earliest mass transformations of the world's surface. The next layer of the story begins when the atmosphere itself becomes the battleground. Oxygen is so closely associated with life that it is easy to forget it once behaves like a planetary toxin. The air humans breathe, the gas that fuels animal metabolism and helps power complexity itself, does not begin as Earth's obvious blessing. It arrives as a disruption. The surface version of the story says photosynthetic life gradually enriches the atmosphere with oxygen, making the planet more suitable for advanced organisms. The deeper truth is more violent. For much of early Earth's history, free oxygen is scarce, and the biosphere is built around other chemical rules. Microbial life thrives in oceans and sediments under conditions where oxygen is unnecessary and in many cases lethal. Then, over immense spans of time, certain microbes begin releasing oxygen through photosynthesis, and what starts as a metabolic byproduct becomes one of the most consequential planetary transformations in Earth's history. The obvious explanation is that more oxygen means a better world. The real problem is that before oxygen becomes a foundation for later complexity, it acts as a corrosive assault on the existing order. To many early organisms, oxygen is not nourishment. It is poison. Highly reactive, eager to participate in chemical reactions that damage delicate cellular machinery, it threatens life forms adapted to a very different atmosphere and ocean chemistry. This is why the rise of oxygen is not simply a triumph. It is a regime change. The new metabolic strategy does not peacefully add itself to the old Earth. It begins rewriting the terms of survival. At first, the oxygen released into the oceans does not linger freely for long. It finds substances ready to consume it. Dissolved iron in seawater reacts with it, forming iron oxides that sink and accumulate in vast layered deposits on the seafloor. These banded iron formations remain among the great mineral records of Earth's changing chemistry, evidence that for long stretches the planet is busy neutralizing a substance that life itself is manufacturing. This only looks like geology from a distance. It is actually a planetary struggle over what kind of world can continue to exist. Oxygen is being made faster and faster, but the Earth of that time still has enormous sinks ready to absorb it. Rock, seawater, volcanic gases, reduced compounds in sediments, all of them help delay the atmospheric breakthrough. That delay is crucial. It means the transformation is not sudden in the human sense, but once the balance finally tips, the change is still profound. The oceans and crust can no longer swallow all the oxygen being produced. It begins to accumulate in the atmosphere. And with that accumulation, an older Earth starts to die. This is the event often referred to as the Great Oxidation Event, though the word event can mislead by sounding brief or clean. In reality, it is a drawn-out planetary restructuring unfolding over geological time with consequences that reverberate through chemistry, climate, and evolution. Anaerobic organisms, which dominate much of the earlier biosphere, are pushed into retreat extinction or isolated refuges where oxygen remains absent. The world becomes more hostile to the life that had once made it their own. One of Earth's greatest future advantages is introduced as a mass ecological crisis. The achievement is real. The cost is larger. Because oxygen does more than poison. It changes the atmosphere's behavior. It alters which gases remain abundant, which reactions dominate, and how much heat the planet retains. One likely consequence is a reduction in methane, a powerful greenhouse gas that had helped warm the young Earth under a dimmer sun. Oxygen reacts through atmospheric chemistry in ways that diminish methane's influence. And once methane falls, the climate may cool sharply. The exact details remain an area of scientific investigation, and restraint matters here. Earth's deep past is reconstructed from fragmentary evidence, isotopic clues, rock records, and models that continue to improve. But the broader conclusion is difficult to escape. The rise of oxygen is tied not just to biological upheaval, but to climatic upheaval as well. What looks like chemical progress may also help trigger severe planetary cooling. This is the deeper pattern again. Every apparent stabilization on Earth comes wrapped in new danger. Life makes oxygen. Oxygen opens the path to more energetic metabolisms and eventually complex multicellular organisms. But oxygen also corrodes old biological orders, rewrites the air, and may help destabilize the climate that allowed the earlier biosphere to flourish. Earth does not move toward habitability in a straight line. It keeps passing through narrow gates that close older possibilities as they open new ones. Oxygen also enables something else of immense importance. Once enough accumulates in the atmosphere, it contributes indirectly to the formation of an ozone layer in the upper atmosphere. Ozone absorbs much of the sun's harmful ultraviolet radiation, offering protection that later helps life expand more safely near the surface and eventually onto land. The story on the surface is that oxygen makes breathing possible. The story underneath is that oxygen helps redesign the planet's relationship with sunlight itself. A microbial innovation changes not just metabolism, but atmospheric shielding. This is what makes Earth harder to think about in simple terms. A tiny organism harvesting light in shallow water ends up influencing global mineral deposits, greenhouse balance, atmospheric composition, radiation shielding, and the future evolutionary horizons of the biosphere. Small life does not remain small in its consequences. But even this new oxygen-rich world is not secure. It is more chemically dynamic, more biologically ambitious, more open to complex forms of life, yet still vulnerable to collapse. The climate can still swing, ice can still advance, feedbacks can still amplify stress. In fact, some of the same planetary interactions that make Earth recoverable also make it capable of approaching extremes that look almost terminal. The rise of oxygen does not end the age of fragility, it deepens it. Because once the atmosphere and climate have been rewritten, Earth becomes capable of another astonishing state, one that sounds almost incompatible with the continuity of life itself. A world locked in ice on a near-global scale, a planet that seems to come terrifyingly close to losing the very fluidity that made biology possible. The next layer of the story begins when the living world that has already survived fire impact and atmospheric poisoning faces something quieter and in its own way just as unforgiving. Cold enough to stop oceans at the surface. Cold enough to make Earth look almost dead. Earth does not need to explode to become unrecognizable. It can fail quietly by reflecting too much sunlight, locking too much water into ice, and letting feedback turn cooling into a planetary trap. The surface version of habitability imagines a world balanced between heat and cold. The deeper truth is that Earth's climate system contains mechanisms capable of amplifying disturbance until the planet moves frighteningly close to conditions incompatible with surface life. One of the starkest examples is the idea that at several points in the deep past, Earth may have entered near-global glaciations so severe that ice spreads toward low latitudes, and much of the planet begins to resemble a frozen world. This is often described through the snowball Earth hypothesis. The details remain debated, especially the exact extent of the ice cover and how much open water persists. But the central revelation is already enough. Earth appears capable of approaching a state in which the mobility of water that makes so much else possible is shut down at the surface. The obvious explanation is that ice is just another climate phase. The real problem is feedback. Ice is bright. It reflects sunlight efficiently. As cooling expands, ice cover, more incoming solar energy is reflected back into space, which promotes further cooling, which grows more ice, which reflects more light. This only looks like weather from a distance. In planetary terms, it is a positive feedback loop with the power to turn a chill into a crisis. Once ice advances far enough, especially into lower latitudes, recovery becomes harder because the planet is no longer absorbing as much solar energy where it needs it most. Earth's climate does not simply drift colder. It can become structurally biased towards staying cold. That is why these ancient glaciations matter so much. They reveal that Earth's long habitability is not built on the absence of extreme feedback, but on the fact that extreme feedback does not always get the last word. The causes of such glaciations are complex and likely involve multiple factors: continental arrangements that alter weathering and ocean circulation, atmospheric carbon dioxide, drawdown solar luminosity, lower than today, and changing chemistry in the air and oceans. But whatever chain dominates in any given interval, the outcome exposes a planet that is far less gently self-regulating than the simple story suggests. Earth can overshoot. It can move toward dangerous extremes, not because one protection fails completely, but because several ordinary processes reinforce one another too well. The same carbon cycle and weathering machinery that stabilize climate over long spans can, under certain configurations, help drive cooling far enough to become self-deepening. The system that usually saves the planet can, under different circumstances, nearly trap it. That is the contradiction again. Earth's resilience and Earth's vulnerability are built from many of the same parts. Yet the deeper shock is not only that Earth may freeze so extensively, it is that life persists through such intervals at all. If the surface oceans are sealed beneath ice over vast regions, if sunlight access is reduced, and if climate becomes brutally hostile, then the ordinary expectation is collapse. Ecosystems contract, habitats vanish, evolutionary pathways are cut off. But the story does not end there. Microbial life likely survives in refuges, perhaps in open water regions, perhaps near hydrothermal systems, perhaps beneath ice, perhaps in sediments and chemically active niches where the planet remains locally alive even while globally transformed. What matters is not the exact map of every refuge which remains uncertain, but the principle it reveals. Earth's biosphere does not survive because crisis stops at the edge of danger. It survives because some fraction of the living system can retreat into narrow shelters until the larger planet changes again. Stability on Earth often means recoverability after collapse, not immunity from it. And recovery from a snowball state likely depends on one of the same deep forces that had seemed dangerous earlier: volcanism. When weathering is suppressed beneath extensive ice cover, one of the major pathways by which carbon dioxide is removed from the atmosphere weakens dramatically. Volcanoes, however, can continue releasing carbon dioxide over long periods. If the planet remains frozen long enough, greenhouse gases can accumulate because the usual drawdown mechanisms are slowed. Eventually, the balance may shift. Warming strengthens. Ice begins to retreat. Darker surfaces are exposed. More sunlight is absorbed. Another feedback loop now runs in the opposite direction, and deglaciation can accelerate violently. The planet that looked locked may still contain an exit, but the exit is not gentle. It may involve rapid warming, intense runoff chemical upheaval in the oceans, and a world suddenly lurching from one extreme toward another. The obvious explanation is that Earth avoids permanent freezing because it has a robust climate system. The deeper explanation is that Earth avoids permanent freezing because its geologic engine keeps operating beneath the ice and eventually overwhelms the freeze with accumulated greenhouse pressure. Again, the calm surface image fails. Earth remains habitable over deep time, not because it rests in equilibrium, but because it keeps escaping from disequilibrium before the escape routes close. Severe environmental stress can reorganize evolution. After global crises, ecological space changes. There is ongoing debate over how directly these frozen intervals connect to later evolutionary developments, and certainty would be dishonest. But the pattern is clear enough: catastrophe on Earth does not merely destroy, it rearranges the terms under which the next world emerges. The surface story is that life survives despite planetary crisis. The deeper story is that planetary crisis helps define what forms of life, climate, and chemistry come next. Earth is not a smooth ascent toward complexity. It is a sequence of thresholds crossed under pressure, and that pressure reveals something essential. The planet's long-running habitability is not a serene gift preserved from disturbance. It is a managed instability repeatedly broken and rebuilt. That makes the next question unavoidable. If Earth can be poisoned by oxygen frozen shut and still recover, then what exactly is the nature of its stability? Is it true balance, or only a temporary success of competing feedbacks that have not yet failed at the same time? The next layer of the story begins there, where resilience stops looking like safety and starts looking like a precarious truce, maintained between systems that never fully stop pulling against one another. Earth remains habitable not because it is safe, but because it is recoverable. That is the harsher form of the truth. The surface story says Earth is a balanced world, a planet with ocean's atmosphere, magnetic shielding, and geological activity arranged in a stable order that naturally supports life. The deeper truth is that this order is less like a permanent design and more like a temporary truce maintained among forces that could, under slightly different conditions, push the planet towards sterility, suffocation, freezing, overheating, or ecological collapse. Earth's long success is real. The cost of that success is constant negotiation. What matters is not that the planet avoids every crisis. It is that crisis does not usually arrive in a combination or duration severe enough to end the entire experiment. That distinction is everything. Because when Earth appears stable, it is often only because the timescale of instability is larger than the scale on which humans instinctively measure danger. Climate feedbacks operate over thousands to millions of years. Plate tectonics reshapes the carbon cycle over spans longer than civilizations, longer than species, sometimes longer than the apparent permanence of oceans and mountains themselves. Life modifies atmosphere and sediments, not in moments of revelation, but in accumulations so slow that the transformation looks invisible until it is complete. The obvious explanation is that Earth is a world in equilibrium. The real explanation is that Earth is a world full of opposing imbalances that sometimes counteract one another well enough to keep conditions usable. Volcanoes release carbon dioxide. Weathering removes it. Ice reflects sunlight and cools the planet, but greenhouse gases push back in the other direction. Life draws carbon into biomass and sediment, but decay and metamorphism return it. Oceans absorb heat, then redistribute it. Tectonics destroys crust and makes new crust. The atmosphere changes. Then chemistry, geology, and biology begin answering that change. Earth is not held together by one stabilizer. It is held together by many partial stabilizers that do not always agree, do not always work quickly, and do not always protect the same forms of life. This only looks like harmony from a distance. Up close, it is managed tension. That is why the history of Earth contains both continuity and rupture. The planet preserves liquid water over billions of years, yet repeatedly subjects the biosphere to conditions that seem almost intolerable. It maintains a breathable atmosphere for animals, yet allows oxygen first to emerge as poison. It supports complex ecosystems, yet periodically drives large portions of them into extinction. Stability on Earth does not mean gentleness. It means the system bends, absorbs, breaks parts of itself, and then rebuilds before the damage becomes total. Even mass extinctions belong inside this harder picture. They are not proof that Earth's habitability fails completely. They are proof that Earth's habitability is unevenly distributed across forms of life regions and eras. A planet can remain alive while much of what lives on it dies. That is an unbearable fact at the human scale, but it is central to the planetary one. The achievement is real. The protection is partial. There are many ways to be habitable, and some of them are brutal. Asteroid impacts flood basalts, abrupt shifts in ocean chemistry, collapsing food webs, greenhouse episodes, glaciations and changing sea levels all reveal the same underlying pattern. Earth does not hold a single ideal state and defend it. It moves through different states, some richer, some harsher, some favorable to one kind of complexity and hostile to another. Life persists by adapting to moving boundaries, not by inheriting a fixed paradise. And yet, the existence of those moving boundaries is also what makes higher complexity possible in the first place. A world of absolute geological stillness might be calm, but it might also be chemically exhausted. A world with no climatic feedbacks might be simpler, but it might not remain habitable under a brightening sun. A world with no disturbance might protect current life, but it might also starve evolution of the selective pressures and environmental diversity that drive innovation. This is the contradiction at the heart of Earth's success. The same restlessness that makes the planet dangerous also helps make it fecund. Diversity does not arise on a blank, unchanging canvas. It arises in a world with gradients, disruptions, niches, barriers, and openings. Continents split and join. Coastlines move. Mountains rise. Seas advance and retreat. Atmospheres shift. Ecosystems are isolated, stressed, reunited, and forced into new arrangements. Earth's instability is not separate from the richness of life. In important ways, it helps produce it. But that richness comes with a price. The more intricate the biosphere becomes, the more relationships it contains that can be broken. Microbial life can survive in buried rock deep sediments, acidic springs, frozen niches, and dark oceanic crust. It can retreat and wait. Complex life is less forgiving. It depends on oxygen levels, temperature ranges, nutrient cycles, food webs, and environmental continuity that are much harder to rebuild once lost. In other words, as Earth becomes more biologically elaborate, its capacity for wonder grows alongside its capacity for fragility. The surface story is that complexity represents progress. The deeper story is that complexity represents dependence. Forests, reefs, grasslands, planktonic blooms, migratory systems, and later animal civilizations all rely on chains of stability, narrower than the microbial world that comes before them. Earth's resilience therefore contains a cruel asymmetry. The planet itself may recover from enormous shocks. The life forms that currently define an era may not. That is why habitability cannot be treated as a single yes or no property. Earth can remain habitable in the broad planetary sense while becoming lethal to much of its complexity in the biological sense. And once that difference becomes visible, the next layer of the story opens. The long history of Earth has been building toward forms of life that are more active, more sensitive, more interdependent, and more capable of reshaping their environments. That development expands what the planet can do. It also narrows what those organisms can survive. The deeper Earth becomes, the more beautiful it gets. The more beautiful it gets, the easier it is to damage what has taken so long to assemble. The next stage of the story begins when complexity itself becomes one of the planet's greatest achievements and one of its greatest vulnerabilities. Earth's greatest biological achievement is also one of its deepest exposures. The surface story says, evolution moves from simple life toward more advanced forms, as if complexity is the natural reward of a stable world. The deeper truth is more demanding. Complexity is not just abundance, variety, or beauty. It is dependence layered upon dependence. It is energy flowing through longer chains, bodies built from more specialized parts, ecosystems stitched together by more precise relationships, and survival tied to conditions far narrower than those tolerated by the hardier microbial world that comes before. The obvious explanation is that a richer biosphere makes Earth stronger. The real problem is that a richer biosphere also makes Earth easier to wound. Early life can endure extremes that later life often cannot. Microbes survive in boiling vents, frozen rock acidic pools, buried sediments, and lightless depths. They persist in places where complexity would collapse almost immediately. But as oxygen accumulates, as cells cooperate, as multicellular organisms emerge, and as ecosystems begin to thicken into webs of predation, symbiosis, competition, and nutrient exchange, the living world becomes more expressive and more fragile at the same time. This only looks like progress from a distance. Up close, it is a trade. More capability in exchange for more vulnerability. Complex organisms gain mobility, specialization, sensation, coordination, and eventually intelligence. They also inherit narrower margins for failure. They need oxygen within usable ranges. They need temperatures that do not drift too far. They need food that itself depends on other food. They need habitats structured enough to support breeding, migration, shelter, and timing. A microbial biosphere can survive as a scattered persistence. A complex biosphere needs continuity. It needs enough stability not merely to exist, but to connect. That is the harder threshold Earth eventually crosses. The seas do not simply host life. They begin hosting layered ecologies. Sunlight drives photosynthesis in surface waters. Microscopic producers support grazers. Grazers support hunters. Nutrients circulate through currents, upwellings, and seasonal rhythms. On land, once life moves ashore, the same escalation follows. Plants alter soil weathering and atmospheric chemistry. Root systems fracture rock. Organic matter accumulates. Fungi link living systems to dead material and back again. Insects, vertebrates, forests, grasslands, and reefs emerge not as isolated wonders, but as interlocking systems. The story on the surface is biodiversity. The story underneath is interdependence. A reef is not only coral. A forest is not only trees. A grassland is not only grass. Each is a timed arrangement of chemistry, climate, mutual tolerance, energy flow, and ecological memory. What matters is not that Earth becomes full of life. It is that life becomes organized enough to depend on forms of stability that can disappear much faster than they are built. That asymmetry is central. It can take millions of years for ecosystems to deepen, diversify, and occupy new niches. It can take far less time for climatic disruption, ocean acidification, rapid warming, cooling, or habitat fragmentation to tear those arrangements apart. Evolution can refill emptiness, but not on the schedule of the organisms caught inside the loss. Earth's biological richness therefore rests on a paradox. The more elaborate life becomes, the more it depends on the continued success of atmospheric balance, ocean circulation, nutrient cycling, and climate buffering mechanisms that remain at their core planetary processes beyond the control of any one species within the system. Complex life inherits the planet's old instability, but now with more to lose. Extinction events reveal this brutally. They are not mere interruptions in an otherwise steady ascent. They are reminders that the biosphere's complexity can be reset, thinned, and restructured when stress outruns resilience. Some crises remove dominant groups and open pathways for others. Some collapse marine systems, terrestrial systems, or both. The details differ across eras, but the lesson repeats. Biological success does not free life from Earth's volatility. It binds life more tightly to it. And yet, complexity also feeds back into the planet in new ways. Forests alter albedo water cycling and carbon storage. Marine organisms build shells, reefs, sediments, and chemical reservoirs that affect ocean and atmospheric history. Buried organic carbon changes climate over deep time. The biosphere does not merely become more vulnerable, it becomes more influential. The living world grows strong enough to change erosion rates, atmospheric composition, and surface reflectivity. Earth is no longer simply a planet with life on it. It becomes a world whose face chemistry and climatic behavior are partly co-authored by living systems of increasing scale and sophistication. The achievement is extraordinary. The cost is dependence spread across wider and wider networks. The arrival of animals intensifies this pattern further. Nervous systems, locomotion, predation, sociality, memory, and eventually culture introduce new forms of adaptation, but also new forms of fragility. A predator cannot survive if prey collapses. A migratory species fails if roots break. A reef community dies if temperature thresholds are crossed for too long. A forest falters if rainfall rhythms shift beyond recovery. Complexity is not only what a biosphere can do, it is what a biosphere can no longer survive without. This is why Earth's living abundance should not be mistaken for invulnerability. The lush world is often the vulnerable world, because lushness means many narrow conditions are being met at once. And out of that tightening web, one development matters more than any other for the next stage of the story. Somewhere within this long planetary experiment, a species emerges that does not merely participate in ecosystems, but begins to perceive systems, model them, extract from them at scale, and reshape them intentionally. Intelligence of that kind is not just another adaptation. It is a new force entering the biosphere from inside the biosphere itself. Earth has already been changed by impacts, tectonics, microbes, oxygen, ice, and mass extinction. Now it will be changed by a form of life that can understand the world as a system and still destabilize it. The next layer begins when complexity stops being only vulnerable and becomes active enough to alter the conditions on which it depends. Earth has been altered by life before, but never by a form of life that can measure the atmosphere and still change it faster. That is the next fracture in the story. The surface explanation says, humans are simply one species, among many another branch of Earth's evolutionary tree, another animal shaped by climate geography and biology. The deeper truth is that humans become something more consequential than a successful organism. They become a planetary force that acts with memory, foresight, extraction symbols, stored knowledge, and technological leverage. The obvious explanation is that intelligence gives a species better tools for survival. The real problem is that intelligence also gives a species the power to reorganize the systems that make survival possible in the first place. For billions of years, Earth is changed by processes that do not intend their consequences. Tectonics does not choose. Microbes do not plan. Ice does not calculate. Even mass extinction is blind. But with humans, intention enters the system. Fire is controlled. Landscapes are burned and cleared. Rivers are redirected. Species are moved beyond their old barriers. Fossil carbon buried over immense spans of time is unearthed and returned to the atmosphere in a geological instant. What matters is not only that humans affect the planet. Many organisms affect the planet. What matters is the speed, reach, and self-awareness of the effect. Human beings become the first known component of Earth's biosphere capable of reading, deep time reconstructing climate history, discovering the carbon cycle, measuring atmospheric change, and then continuing to intensify that change anyway. This only looks like power from a distance. Up close, it is a new form of planetary risk, a species intelligent enough to understand consequences, dependent enough to suffer them, and expansive enough to spread them everywhere. For most of human history, the scale remains comparatively local. Hunter-gatherers alter ecosystems sometimes substantially through hunting, burning, and movement. Agriculture then transforms the relationship between life and land more deeply. Forests are cut. Wetlands are drained. Soil is domesticated into production. A few plants and animals are drawn into tight association with human needs, and in that association, entire landscapes are simplified, disciplined, and reshaped. Cities appear. Surplus accumulates. Trade extends ecological reach beyond immediate terrain. The story on the surface is civilization. The story underneath is energy capture and environmental conversion. More sunlight is intercepted by crops. More water is redirected by irrigation. More biomass is claimed by one species and the organisms bound to it. Human history is not separate from Earth system history. It is one of its later chapters. Yet the sharper break comes with industrialization. Coal, oil, and gas are not merely fuels. They are ancient sunlight, compressed into geological storage by vanished ecosystems and buried time. To burn them is to reopen old carbon vaults and inject their contents back into atmosphere and ocean at a rate natural long-term balancing mechanisms struggle to absorb. The obvious explanation is that industry gives humanity heat, motion, chemistry, transport abundance, and modern power. The deeper explanation is that industry allows one species to spend Earth's ancient biological inheritance in exchange for a very brief burst of planetary transformation. Carbon dioxide rises, methane rises, nitrogen cycles are rewritten by synthetic fertilizer, forests shrink, oceans warm, ice retreats. Sea level begins its slow but relentless response. Species face a new pattern of pressure, not because the planet has entered one of its blind ancient crises, but because one part of the biosphere has become energetic enough to trigger crisis from within. The achievement is real, the cost is larger. Humans have increased food production, reduced some forms of suffering, expanded lifespan in many places, mapped the genome landed machines on other worlds, and turned abstract scientific knowledge into working infrastructure. But every layer of that achievement depends on a biosphere, a climate range, a hydrological cycle, and a geochemical baseline that human activity now actively perturbs. This is the contradiction that makes the human chapter so dangerous. The same intelligence that allows deep understanding also enables deep destabilization. The same technological system that reveals Earth's fragility becomes a mechanism for testing that fragility at full scale. And unlike volcanic episodes or asteroid impacts, the disturbance is not external to human life. It is inseparable from the systems feeding cities, powering industry, organizing economies, and sustaining billions of people. There is no clean line between cause and victim. Human civilization is both. This is why the old image of Earth as a stable stage for human history is no longer adequate. Humans are now part of the machinery influencing atmosphere, albedo biodiversity, ocean chemistry, and sediment flow. Dams trap rivers. Fishing alters marine food webs. Mining relocates matter on continental scales. Plastics accumulate in seas and soils. Concrete, asphalt, and steel become signatures of a species writing itself into the geological record. Even domesticated animals and cultivated plants begin to outweigh wild vertebrate communities in ecological significance. The living surface of the planet is not merely occupied by humanity. It is being reorganized around humanity's metabolism. Yet this power remains constrained by old planetary truths. Climate does not negotiate with ideology. Water cycles do not care about markets. Soil exhaustion does not pause for political convenience. Ocean acidification is not impressed by technological confidence. The real problem is not that humans are changing Earth. Earth has always changed. The real problem is that humans are changing it while depending on unusually narrow, Holocene-like conditions that help agriculture, coastlines, rainfall systems, and complex global infrastructure remain predictable. Civilization thrives not in any habitable world, but in a relatively stable one. That means the more successfully humans dominate the biosphere, the more tightly they bind themselves to maintaining the very stability they are capable of disrupting. Earth has carried life through fire, poison, ice, and impact. It may carry life through the human age as well. But that is not the same as carrying human systems intact. The planet can remain alive while the arrangements humans rely on become harder, harsher, and less forgiving. And behind even this self-made danger stands a larger pressure that no civilization can negotiate away. The favorable world humans inherit is not permanent. It exists inside a cosmic window shaped by solar evolution, atmospheric chemistry, internal planetary heat, and the temporary success of overlapping feedbacks. The next layer of the story begins there, where the question is no longer whether humans can destabilize Earth, but whether Earth's long era of unusual generosity is ever something that could have lasted forever at all. The most dangerous illusion Earth creates is permanence. Mountains seem permanent. Oceans seem permanent. The atmosphere feels permanent because every human breath arrives inside it without negotiation. Even climate, despite all its moods, is often imagined as a background condition that can change in detail while preserving the broad habitability of the world. But the deeper truth is more severe. Earth's long-lived hospitality is not a permanent state written into the nature of the planet. It is a window, a remarkably durable window, yes, but still a window bounded on one side by formation and violence, and on the other by cosmic change that no biosphere can bargain with forever. The obvious explanation is that Earth is habitable because it orbits at the right distance from the Sun. The real problem is that the Sun does not stay the same. Stars evolve. Our Sun, though relatively stable compared with far more massive stars, is not a fixed lamp hung above an unchanging world. Over immense spans of time, as hydrogen fuses into helium in its core, the internal structure of the star slowly changes, and with that change, its luminosity gradually increases. The Sun of deep planetary history is dimmer than the Sun of today. The Sun of the far future will be brighter still. This only looks like a small correction from a distance. In planetary terms, it means Earth's habitable era must constantly be renegotiated against a rising energy input. The remarkable part is not that Earth begins inside a favorable range. The remarkable part is that its climate system, carbon cycle, oceans, atmosphere, and geology managed to keep the surface usable, while the star itself slowly changes the terms of the arrangement. That is why distance alone is never enough. Earth is not motionless inside a perfect zone. It is surviving inside a moving problem. Earlier in its history, when the Sun is fainter, Earth faces a different paradox. How does a young world avoid freezing under a weaker star? That puzzle likely involves greenhouse gases, atmospheric composition, cloud behavior, ocean heat, transport, and feedbacks that remain areas of active scientific reconstruction. But the broad lesson is already clear. From early on, Earth's habitability depends not on static placement, but on dynamic compensation. Later, as the Sun brightens, the compensation must work the other way. Carbon dioxide is gradually drawn down over long timescales through weathering and related geological processes, helping counter increasing solar luminosity. The achievement is extraordinary. The cost is that this strategy cannot continue forever. A planet can keep reducing greenhouse warming only until it begins to starve itself of the very gases many life forms need. There is no endless room for adjustment. The balancing act narrows. Long before the Sun swells into its red giant phase, long before Earth faces the final violence of stellar evolution, habitability in the familiar sense begins to erode. As solar output rises, evaporation intensifies, weathering shifts, ocean chemistry changes, and the atmosphere moves toward conditions less favorable for complex biospheres. On very long timescales, carbon dioxide may fall so low that photosynthetic life as we know it struggles to persist. Plants do not merely like carbon dioxide, they depend on it. Remove too much of it in the name of climate stabilization, and the biosphere pays a different price. This is the contradiction again at cosmic scale. The same feedbacks that help preserve habitability through one era become part of the pathway by which later eras lose it. The story on the surface is that Earth regulates itself. The story underneath is that self-regulation is only possible within certain boundaries, and those boundaries are moving. Eventually, as the sun continues brightening, Earth may cross into a moist greenhouse state or related pathways of severe warming, in which the oceans become increasingly vulnerable. More water enters the upper atmosphere, where sunlight can break water molecules apart and allow hydrogen to escape to space. Over immense spans, a world of oceans can become a world that is losing the raw material on which its surface life depends. That is one of the hardest truths in the entire story. Even water, the great mediator of Earth's habitability, is not guaranteed forever. The seas that seem like the deepest expression of permanence may belong only to a long middle chapter. Nor is the sun the only clock running. Earth's own interior is slowly cooling. The planet remains geologically active because it still carries ancient heat and ongoing radiogenic heat production, but internal vigor is not infinite. Over sufficiently long timescales, tectonic behavior, volcanic outgassing, magnetic field generation, and deep recycling may all change as the internal energy budget evolves. The exact sequence and interaction of these long-term changes remain complex, but the larger implication is unmistakable. Earth's habitability depends on a stack of processes that are not timeless. The sun changes, the interior changes, the atmosphere changes, the biosphere changes, oceans shift, continents rearrange. Every major pillar of the habitable world belongs to history, not eternity. This is what transforms Earth from a comforting fact into a rare event in progress. The planet does not merely host life. It hosts a temporary alignment of star orbit, water, rock, air feedback, and time. Human beings happen to exist inside that alignment late enough to inherit billions of years of planetary preparation, yet early enough to imagine the arrangement as normal. It is not normal. It is a phase. A rich one, a magnificent one, but still a phase. The deeper irony is that the apparent durability of Earth's habitability may be exactly what makes its finitude harder to feel. A window lasting billions of years is long beyond human instinct, but against stellar and cosmic time, it is still a window. And once that becomes visible, the meaning of the present changes. Earth stops looking like the obvious destination of planetary history and starts looking like a brief interval in which matter, under very special conditions, becomes ocean, atmosphere, cell, forest, animal, and thought, before the larger machinery moves on. The next layer of the story begins with that pressure. If Earth's generosity is temporary, even without human interference, then the question is no longer only how the world survives. The question becomes what it means to inherit something both ancient and temporary at once. To inherit Earth is to inherit something already in motion. That is the pressure hidden beneath every idea of home. The surface story says, humanity is born into a finished world, oceans already circulating atmosphere, already breathable soils, already fertile climates, already patterned into seasons, rivers, monsoons, and coastlines. Civilization begins inside this inheritance and then builds upward through language, agriculture, trade, science, and power. But the deeper truth is that none of these foundations are fixed in the way human psychology wants them to be. They are ancient, but not permanent. They are durable, but not guaranteed. They are the temporary products of systems older than humanity and larger than any human institution. The obvious explanation is that human beings are now deciding the future of the planet. The real problem is that humans are deciding from inside conditions they did not create and do not fully control. Earth is not raw material waiting for management. It is an unstable success story already billions of years in progress. That difference matters, because once the planet is understood as a rare alignment rather than a permanent backdrop, human power looks less like mastery and more like interference under uncertainty. Modern civilization is built on assumptions so basic they often disappear from thought. Rain will come within usable ranges. Coastlines will remain where maps place them closely enough for port cities and economies to depend on them. Seasons will be recognizable. Soils will keep producing if managed hard enough. Oceans will absorb shocks without crossing thresholds too quickly. Ice sheets will respond slowly enough to feel remote. The atmosphere will remain chemically familiar. These assumptions are not insane. They are inherited from an unusually stable chapter of Earth history, especially the recent geological past, within which agriculture and civilization expand. But the story on the surface is smaller than the story underneath. The stability humans treat as normal is not normal in any universal sense. It is the latest expression of a planetary balancing act that has broken before, recovered before, and changed character many times. Civilization does not rise on a perfectly stable planet. It rises during a relatively forgiving interval. That makes the present moment harder to face. Because the more human systems optimize themselves around narrow climatic and ecological expectations, the more exposed they become to deviations from those expectations. Cities cluster along coasts and rivers. Agriculture depends on rainfall timing, groundwater and temperature windows tuned to specific crops. Fisheries depend on ocean temperatures, currents, acidity, and food web structure. Infrastructure depends on the statistical behavior of storms, heat, frost, flood, and drought. Economic systems then layer efficiency on top of these already narrow physical requirements, often reducing slack in the name of growth or competitiveness. This only looks like sophistication from a distance. Up close, it is dependence refined into precision, and precision can be brittle. The achievement is real. The exposure is larger. Human beings have built networks of extraordinary reach. A drought in one region can affect food prices continents away. A flood, wildfire, or heat wave can expose fragilities in power grids, supply chains, insurance systems, migration pressures, and public health structures all at once. This is not because Earth has suddenly become dangerous. Earth has always contained danger. It is because civilization has become dense enough, interconnected enough, and optimized enough that climatic and ecological disturbance can propagate through systems never designed for deep planetary volatility. The old planetary instability has found a new target. It is no longer only coastlines, forests, and reefs at risk. It is the human arrangement layered on top of them. There is also a deeper mismatch between timescales. Human politics runs on years. Markets often run on quarters, even days. Infrastructure is financed across decades. But the systems being perturbed include ice sheets, carbon reservoirs, ocean circulation, groundwater depletion, soil formation, and biodiversity loss. many of which operate across centuries to millennia while still capable of producing abrupt local or regional consequences. Humans are therefore living inside a dangerous temporal contradiction. The species is smart enough to detect long-term planetary change, but many of its institutions are still organized around much shorter loops of reward fear, competition, and denial. Knowledge arrives faster than adaptation. Warning arrives faster than restraint. This is not a moral failure in only the simple sense. It is also a structural one. A species evolved for immediate survival and local social worlds now has technological leverage over atmospheric chemistry and planetary heat balance. The scale of action outruns the scale of instinct. Yet even here, the deeper truth is not pure doom. Earth's history argues against easy despair, just as strongly as it argues against easy confidence. This is a planet whose systems have repeatedly bent without fully breaking a world where crisis often reveals hidden capacities for buffering recovery and reorganization. But that historical resilience cannot be misunderstood. Earth's resilience is not a promise that current forms of life, current coastlines, current ecosystems, or current human institutions will be preserved. It is a reminder that the planet can continue through loss. That is a comfort only from the wrong distance. To the biosphere in general, continuation may be enough. To particular species, cultures, and civilizations, it may be catastrophic. This is why the inheritance of Earth carries a burden unlike any other inheritance in human history. Humanity receives not just land resources or a favorable climate, but a narrow and temporary interval in which a rare planetary arrangement remains unusually generous. The question is not whether Earth matters. The question is whether humans can recognize that what they call normal is actually fragile success inherited from deep time. Once that recognition becomes clear, the meaning of Earth expands beyond utility. It is no longer merely the place where human life happens. It becomes the only known world where stone water atmosphere biology and time produce not just life, but memory of life, knowledge of life, and awareness of the conditions that made both possible. The next layer of the story begins there. Because once Earth is understood, not just as a habitat, but as a rare event through which the universe becomes locally aware of itself, the planet's significance stops being merely practical and becomes something much larger. Earth matters in a way that goes beyond shelter. The surface story says it is valuable because it is where humans live, where food grows, where water flows, where air can be breathed, where memory, love, labor, conflict, and civilization take place. All of that is true. But the deeper truth is larger. Earth is, so far as anyone knows, the only place where matter arranges itself into oceans, atmosphere, metabolism, ecosystem, mind, and reflection all at once. It is not just a habitable planet. It is a world in which the universe becomes capable of noticing the conditions that make noticing possible. The obvious explanation is that life on Earth is important because it is rare to us. The real explanation is harder and more unsettling. If Earth truly is rare, then its significance is not sentimental. It is structural. It may represent one of the very few places where chemistry survives long enough, under stable enough constraints, through enough crises to become biology, then complexity, then thought. This only looks poetic from a distance. In planetary terms, it is a claim about what the universe can do under very narrow conditions. Earth is not merely another rock among rocks. It is an arrangement in which fire below water, above gases in between, and time across billions of years generates something that can ask what any of it means. That is not a decorative fact. it changes the scale of the story. Because once a world can produce observers, memory science, and self-awareness, its history is no longer only geological or biological. It becomes epistemic. Earth does not just host rivers and forests and clouds. It hosts beings who map tectonic plates, reconstruct ancient climates, detect exoplanets, split atoms, sequence genomes, and trace their own bodies back to older stars. The planet becomes the site where matter begins building explanations of matter. And that makes its fragility harder to dismiss. The surface value of Earth can be counted in resources: land, fresh water, soil, energy, fisheries, minerals. These are real and necessary. Civilizations rise by organizing them. Economies depend on them. States fight over them. But the story on the surface is smaller than the story underneath. The deeper value of Earth is that it is not merely useful. It is generative. It produces conditions under which novelty can accumulate. It stores memory in rock strata ice cores, tree rings, fossils, and genomes. It supports systems complex enough to evolve beauty with no practical obligation to do so. Coral reefs do not need to be beautiful. Forest canopies do not need to produce awe. The night sky reflected in an ocean does not need to mean anything. Yet on Earth, a world of pressure gradients and mineral cycles gives rise not only to survival, but to perception pattern music, grief theory, and moral imagination. This is what makes Earth's rarity heavier than rarity alone. It is not simply uncommon matter, it is fertile matter, interpretive matter, historical matter. The achievement is real, the risk is larger. Because a world capable of producing intelligence is also a world that can lose the ecological and climatic background against which intelligence becomes civilized, cooperative, and enduring. Earth can remain a living planet and still become poorer in possibility. Forests can shrink, reefs can bleach, ice can retreat, species can vanish, soils can thin, rivers can be overdrawn. The atmosphere can be pushed away from the narrow composition under which agriculture, coastlines, health, and large settled societies flourish. None of these losses require the total end of life to matter profoundly. A world need not become Venus to become less generous. It need not become sterile to become diminished. That is the danger of thinking only in planetary absolutes. The question is not simply whether Earth remains habitable in the broadest sense. The question is what kind of habitable world remains for whom, for how long, and with what losses absorbed along the way. This larger scale also changes how human responsibility appears. If Earth were ordinary, then damage would still matter morally, but perhaps not cosmically. If living worlds were abundant and easily replaced, then the destruction of one biosphere would remain tragic without becoming singular. But if complex, long-lived, ocean-bearing, geologically active worlds are rare, and if worlds that produce reflective intelligence are rarer still, then the significance of Earth expands beyond inheritance and utility into stewardship of an unusual concentration of possibility. Not stewardship in the naive sense of perfect control. Humans do not control tectonics, solar evolution, mass extinction risk, or deep time. But they do influence whether a rare world already shaped by ancient crises is pushed into unnecessary new ones by beings capable of understanding consequences. That is the distinction. Earth's fragility is not a reason for worshipful passivity. It is a reason for disciplined seriousness. The planet is not sacred because it is untouched. It has never been untouched. It is sacred, if that word is to mean anything here, because it is active contingent and unlikely a world where instability keeps producing value faster than destruction has yet erased it. And perhaps that is the final widening of the frame before the end. Earth is not important merely because humans are on it. Humans are important if they are important at all, because they are one recent expression of what Earth has been building through rock-sea atmosphere and evolution for billions of years. The arrow of meaning may point the other way. Civilization does not elevate Earth by using it. Earth elevates civilization by making it possible. Science does not stand above the planet. It is one of the planet's own late emergent acts. Memory, ethics, art, and explanation are not departures from Earth's story. They are among its most improbable outcomes. That is the larger scale. This world of oceans and fire and fragile balance is not merely where the story happens. It is the reason the story can be told at all. And once that becomes visible, only one step remains. The final synthesis is not about whether Earth is beautiful, useful, or rare. It is about how a world that should have failed so many times keeps holding together long enough to become a home, a history, and a question the universe asks through us. Earth should be easier to lose than to keep. That is the final frame. The surface story says, our planet is simply the place where life succeeds, the familiar blue world of oceans, clouds, continents, seasons, and history. But after following the deeper layers, that version no longer holds. Earth is not the obvious outcome of planetary evolution. It is the long survival of a fragile arrangement that has already passed through impacts, infernos, atmospheric transformation, global ice, tectonic restlessness, biological upheaval, and repeated ecological reorganization without letting the entire system collapse into silence. The obvious explanation is that Earth is stable enough to support life. The real explanation is far more demanding. Earth supports life because instability itself is organized into a dynamic balance that repeatedly breaks, repairs, compensates, and reopens possibility before the window closes. This only looks like serenity from a distance. Up close, it is endurance under pressure. The young planet forms from violence. A giant collision likely reshapes it and helps produce the moon. The interior remains hot enough to move metal, lift rock, and power a magnetic shield. The crust refuses stillness and becomes a recycling engine. Water arrives not as decoration, but as a force carrying heat, carving stone, linking air to land to sea. Life begins small, then grows large in consequence, altering the atmosphere, transforming the chemistry of oceans, and eventually poisoning the very world that came before it with oxygen. The planet nearly freezes. It recovers. Complexity rises. It suffers extinctions. It rebuilds. Forests, reefs, soils, climates, and food webs emerge not from peace, but from recovery, repeated often enough to become abundance. Then a reflective species appears inside that abundance, dependent on unusually narrow conditions, capable of reading the planetary past and still capable of destabilizing the planetary present. And behind even that human drama stands the colder truth that the whole generous interval is temporary. The sun brightens. The planet evolves. The window narrows. Earth's habitability is real, but it is not a law. It is a chapter. What matters is not any single miracle in that sequence. It is the layering. Fire below water, above air, between gravity, enough distance, enough motion, enough shielding, enough feedback, enough time, enough. Remove one pillar too early, weaken one cycle too far, alter one protection too badly, and the entire history changes. Earth does not owe its success to one gift. It owes it to a chain of partial successes that overlap long enough to produce a world where chemistry becomes metabolism, metabolism becomes ecosystem, ecosystem becomes intelligence, and intelligence becomes aware that none of it had to last this long. The achievement is real. The improbability is larger. This is why Earth feels ordinary only to those inside it. Familiarity is the disguise worn by rare success. The sea seems natural because generations are born beside it. The atmosphere seems guaranteed because every breath arrives before doubt. The seasons seem inevitable because human memory is short. But the deeper view strips away that illusion. Oceans are not default. Oxygen is not default. Climatic softness is not default. Geological recycling is not default. A biosphere rich enough to produce memory, culture, science, and warning is not default. Earth is not the standard world. It is the world where many dangerous processes fail to destroy one another long enough to create continuity. And that continuity becomes the stage on which everything human unfolds. Not above the planet, inside it, not separate from its systems, dependent on them. Civilization, science, philosophy, art, and love do not stand beyond rock, water, atmosphere, and time. They are among the latest expressions of a planetary balance that should have been easier to break. That is the final reversal. Human beings often imagine themselves as the meaning laid upon Earth. But Earth is the prior meaning that makes human meaning possible. It is the rare world of oceans, fire, and fragile conditions that does not merely host the story. It generates the conditions under which a story can exist, be remembered, and be understood as fragile while it is still happening. Earth, in the end, is not remarkable because it is invulnerable. It is remarkable because it remains generative while vulnerable, coherent while restless living, while under pressure, and beautiful not despite fragility, but through it. A world that should have failed many times. A world that keeps holding together. Long enough for life to emerge, for mind to awaken, and for the universe in one small place to recognize how narrow and extraordinary that holding together really is. Earth is not the promise that the universe is gentle. It is the proof that for a while, gentleness can emerge inside forces that are not gentle at all. Fire does not disappear. Gravity does not soften. The sun does not stop changing. Ice does not forget how to spread. Atmospheres do not remain stable by sentiment. Extinction does not become impossible because life has grown beautiful. The deeper truth is harsher and far more astonishing. This world endures not because danger ends, but because enough of its systems keep answering danger before the whole structure comes apart. That is why Earth feels less like a finished object than a living negotiation among rock, water, air, light, chemistry, and time. And out of that negotiation comes everything that seems far removed from stone and sea forests: memory, language, tenderness, warning, grief, knowledge, and the strange human ability to look at a planet and understand that it did not have to remain this kind for this long. Earth is rare, not only because it carries life, but because it carries continuity. It keeps enough order in place long enough for complexity to deepen, for intelligence to appear, and for that intelligence to discover that home is not a permanent guarantee, but a temporary triumph. The oceans are real. The atmosphere is real. The beauty is real. But none of them are simple. All of them belong to a balance that has survived by remaining active, adaptive, and vulnerable at once. That may be the final meaning of Earth. Not a flawless sanctuary, not an eternal refuge, a fragile world that keeps becoming habitable again and again, long enough to turn matter into life, life into thought, and thought into responsibility. In that sense, Earth is not just where we live. It is the rare condition that makes living knowing and caring possible in the first place.